Welcome to Basics of Finite Element Analysis. This is the 6th week of the current ongoing MOOC course on FEA, and this week we will start with continuing our discussion for 1D heat conduction problem with convective effects. And in today's lecture, we will actually close that topic by solving for a problem, and then in the remaining 5 lectures we will explore beam theory and how it is solved using the finite element method. So, for this lecture we will first write down the equations which we had developed in the last lecture, and the overall governing equation for 1D heat conduction with convective effects was this thing P So, these two terms where beta appears, they are because of the effect of convection. Okay. And for this particular equation, the stiffness matrix elements we had defined were so that is my stiffness element. Then in the force vector, the terms are AQ plus P beta T infinity and because it is the eth element, I have to put a subscript E on all the parameters. And then the Q's, Q1 was Ka del T over del X, and there is a minus sign here at X bar equals 0, and Q2 for the eth element is exactly the same relation, but with a positive sign and evaluated at X equals He, X bar equals He, and these are all X's are in local coordinate system. So, I am not using X, but I am using X bar. And now what we will do is we will actually develop these equations, and we will have a convective boundary condition, but before we handle the convective boundary condition, we will do this problem without having the convective term. Okay. So, in that case, let us assume that beta equals 0, and then we have seen that the shape function. So, if it is a 2 noded element, this is node 1, node 2, length of the element is He, then my approximation function is 1 psi 1 equals 1 minus x bar over He, and psi 2 is equal to x bar over He. So, using these functions, I can also calculate their derivatives, and then my stiffness matrix comes out as, so my overall equation, I will write that for the element is Ka over He times 1 minus 1 minus 1 1, and if I have a linear element, so then the temperature at linear element at first node is T1e and temperature at the second node is T2e, and these are unknowns. So, T1e, T2e, and this equals the f vector, and the values in that vector are a q naught He over 2 1 1 plus Q1E, which is a point load or a point source of heat. Now, suppose I have a bar and for purposes of discussion in this class, I am breaking this bar. So, I am idealizing this as a line. So, the total bar length is L, okay, and I am breaking it up into 3 elements, element number 1, element number 2, element number 3, and the global nodes are 1, 2, 3, 4. Okay. So, I can write 4 sets of equations at the element level, which will look like this, and then using the condition of continuity, 3 sets of equations, yeah, because there are 3 elements, I am sorry, 3 sets of equations at the element level, and then using the continuity condition, and the continuity condition is that T2E in the first element is equal to T1E of the second element. Similarly, T2E of the second element equals T1E of the third element. So, that is one condition. So, I eliminate 2 variables from there, and I also know that whatever is the source term, whatever is the heat generated. So, suppose let us say, so this is my first element and this is the second element, and in reality these 2 elements are sticking at this point, right. So, the heat generated because of Q is expressed here, okay, at node 1 and this is at node 2. So, the total heat which is being generated at this location will be contribution from this side and contribution from this side. So, I add up the contributions at the intermediate nodes from 2 elements. So, I add up the equations the same way we added up equations in case of solid mechanics problem, the same logic. So, if I do all that, my overall equation at the element level, it becomes at the not the element level, at the assembly level, it becomes Ka over He 1 minus 1 0 0 minus 1 2 minus 1 0 0 minus 1 2 minus 1 0 0 minus 1 1. So, this is my global stiffness matrix, a global K matrix, that multiplied by T1, T2, these are my global degrees of freedom which are not known, and this equals a term, a vector attributable to distributed heat load. So, this is 1, 2, 2 and 1 plus point heat sources, which is Q1, and here this will be 0 because the contribution from left side and contribution from right side, it will be balanced, right. What does that mean in context of heat transfer equation? Suppose heat is coming in like this. So, that is something I will call Q21, right, and in the adjacent element the same amount of heat is going out, right. So, that will be Q12, and when I add these 2 heat terms, they will become 0. So, net heat generation is 0. So, at the interfaces these terms will be 0 and here it will be Q4. So, that is my equation at the assembly level. Okay. Now, I see that in this equation I have 4 unknowns T1, T2, T3 and T4, and then I have two more unknowns Q1 and Q4. So, there are a total of 6 equations, 6 unknowns and 4 equations. So, I need 2 extra conditions, and these 2 extra conditions will be gotten through application of the boundary conditions. So, we will solve this equation for 2 different sets of boundary conditions. In case 1, we will say that T, so this is my overall bar which I have broken into 3 elements, right, and here this is my global degree of freedom. So, and this is coordinate is x. So, at x is equal to 0, I say that temperature is T A, and at x is equal to L, temperature is T B. So, I am saying that I have a bar and the temperature at left end is prescribed as T A, and the temperature at right end is prescribed as T B. So, this is one set of boundary conditions. So, if I do that, we will prescribe this T A, this will be prescribed as T A, and this will be prescribed as T B, right. So, now I have, so these are now knowns T A and T B because we know these values. So, now I have 4 unknowns T 2, T 3, Q 1 and Q 4, and I have 4 equations. So, now I can solve for these 4 equations, for these 4 unknowns using these 4 equations. So, we will actually do that. Okay. So, let us say that T A equals, what did I assume, 100 degrees, T B equals 0, and then for sake of simplicity I have assumed a lot of things as unity. So, I say K equals 1, A equals 1, H E equals 1, so that our computation becomes faster, that is all, and Q naught equals 1 and A is also equal to 1. Okay. So, this K A over H E equals 1, so this term and this term is also equal to 1. This term becomes 1 over 2, this term becomes 1 over 2, A Q naught H E over 2 is 1 over 2. So, what we are doing is that we are going to prescribe K A over H E as 1 and the other term, this term as half, and solve for T 2 and T 3. So, we will write down equations from these 4 equations for T 2 and T 3. So, the first equation which is the second equation. So, this is, so first thing what I will do is I will erase this K A over H E because it is nothing but 1. So, that goes away, and this term it becomes half, and if I remove this half and put it inside, so this becomes 0.5 and this becomes 1, 1 and 0.5. So, I will call this equation 1, call this equation 2, equation 3, and this is equation 4. So, what I am going to do is with these prescribed boundary conditions I am going to write equations 2 and 3. So, my equation 2 is minus 1 times T A, and T A is 100. So, it is minus 100 plus 2 times T 2 minus 1 times T 3 and 0 times T 4, and that equals F 2 which is 1 plus Q 2 which is 0. Okay. So, this is my equation 2. The second equation is equation 3. So, I am going to write it is, so that is 0 times T A, so that is 0 minus 1 times T 2 and then 2 times T 3 and then minus 1 times T 4, and T 4 is 0 degrees right, which is Tb. So, this is 0 and this equals again F3 1 plus Q3 0. So, this is my second equation, third equation. So, equation 2 and equation 3. So, I solve for these two equations and I can calculate T2 and T3, and then I can plug these values back in my equations for E1, equations E1 and E2, and I can find the values of Q1 and Q4. So, this is my first case where I have prescribed at both the ends the primary variables, which is 0 and 100 degrees. Okay. Now, what we will do is we will do another case where we will have a convective boundary condition at one end and another source, heat source at the other end, and we will again solve these equations. So, I am going to erase all this, and the second boundary condition is, so case 2. So, in case 2 my boundary condition, so this is all, this also goes away. So, once again in case 2 the boundary condition here is not known temperatures, but at x is equal to 0 I know how much heat I am injecting into the system. So, that is minus K A del T over del x at x is equal to 0 is some constant G naught. I know that so at this point at x is equal to 0 I am pumping some heat into the system, and the value of that heat is G naught. Okay. That is what this physically means, minus K A times dt over dx. dt over dx is temperature gradient, K is conductivity, A is area of cross section. So, that is the amount of heat transferred because of temperature difference, right. And at this point at x is equal to L, the boundary condition is that K times dt over dx. So, one thing I would like to do is that instead of partial derivatives I will express them as total derivatives, because the only variable left is now x, temperature is not there. So, partial derivative is same as total derivative. So, on the right side at x is equal to L, the boundary condition is K dt over dx plus beta T minus T infinity at x is equal to L, and this I say is 0. So, what does that mean? That there is some convective transfer happening. This K dt over dx is heat which is going out, right, and that equals the convective heat transfer, that equals the convective heat transfer. So, now we will see how to account for this convective heat transfer in our boundary conditions. So, once again my 4 equations, and we still assume that A is equal to 1, Q naught equals 1, He equals 1, and what else, and we will K equals 1. So, these equations are still valid. Okay. So, BC1 is minus Ka del T over del x at 0 equals G naught, and we know that the definition of Q1 is this thing. Okay. So, this term becomes G naught. The second boundary condition BC2 is K A, and I think I messed it up, this should be complete total derivative dt over dx plus beta T minus T infinity equals 0. Now, what I do is this equals Q2, right. So, I express it as Q2 equals minus beta, or I can express it as beta times T infinity minus T, and this is at x is equal to L, and at x is equal to L, this is beta times T infinity minus T4, because at x is equal to L, temperature is T4. Okay. So, I replace this Q4 by this term beta T infinity minus T4. Agreed? This should be Q4. And I missed this A term here, so this A also should be there. So, what I have seen is that I have replaced Q1 by G naught, and I have replaced Q4 by beta times T infinity minus T4. Okay. Now, once again, in these four equations, these are four equations, and I have now four unknowns. On the left side, I have T1, T2, T3, T4, these are four unknowns. On the right side also, there is no unknown which is extra, because I know beta, I know T infinity. T infinity is the temperature of air far away from the fin or this thing, and T4 is an unknown. So, but that is already accounted for. So, four equations, four unknowns. So, the next step which I do is that I transfer this T4 on the left side. I transfer T4 to the left side, and when I transfer it, so first step was replacing Q4 by this term, and now I transfer this. So, on my right side is I still have beta times T infinity, and on my left side I get an extra term beta here. Okay. So, the effect of convective heat transfer at the end of the bar is accounted by changing or modification by because of modification of this K matrix. So, beta comes here, and now I can solve these four equations for four unknowns in a fairly straightforward way. So, this is what I wanted to discuss in context of heat conduction and equation, which also has a convective heat transfer term, and this captures or covers this particular topic. In the next class, we will start discussing the beam theory and how we can use finite element analysis to solve beam related problems. Thank you very much.